So let's talk a little bit about actually expanding out the binomials then. So there's a general expansion, 1 plus x to the power of anything. So it's power of n. So it'll be 1 plus x times 1 plus x times 1 plus x plus times 1 plus x 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 times 1 plus x, whatever n is, that many times. When expanding parentheses, here's the really cool thing. What we're basically doing when we expand parentheses is we choose a term from each individual parenthesis and multiply it together. Yeah. Now, normally if we just got a simple binomial, we might go, oh, what's x plus 2 times x plus 3? And remember the first time you learned to do that, the FOIL method or whatever you called it, but you said, okay, I'll multiply the first one with the first one and the other one. So you grabbed a term in each, multiply them together. And then you went, oh, outside, I'll grab the outside ones and multiply them together. I'll grab the inside ones, multiply them together. I'll get the last ones, multiply them together and add them all up. Well, that's the same, doesn't matter how many parentheses you do. To get each individual term, you're choosing one term from each, multiplying them together. So, to work out x cubed, how could I get x cubed? Well, here's one example. I could choose x from the first one, 1 from the second one, x from the third one, then 1 and 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 then the very last one I'll choose x. And I'll end up with x cubed when I expand that out. But of course that's just one way I could have got x cubed. How many different ways could I do that? And this is where we're going back to permutations, combinations. Okay. So how many different ways could we end up with x cubed? In other words, how many ways can I choose 3 of those parentheses to pull x out of? So out of the n parentheses, I'm going to choose 3 of them to use the x. All the other ones I'm going to take 1 from. How many ways could I do that? NC3. So those coefficients in your binomial expansion always turn out to be the same as the number of combinations. Very convenient that the pronumeral we use for that is capital C, because capital C could stand for combinations, but it also could stand for coefficients. How cool is maths? All right. So, if we now want to get a general expansion of a binomial, yeah, Pascal's triangle was great, a bit overrated, should be Simmons' triangle. But we don't need it. Oh yeah, it's good if you got a small number, but if you got a large number like 21, it takes a while to write all the numbers out. But what we could do is say, well look, we know that in 1 plus x, so think of the simplest expansion we could have, 1 plus x to the power of k. If I want to find the coefficient of x to the k, it's got to be nck. Of those n parentheses, I'm going to choose x out of k of them. So how many ways can I do that? nck. Now, an alternative notation that we sometimes use in this binomial theorem is this notation with parentheses here. Notice it's not a fraction, there is no vinculum there. It's just n. So it's I guess a shorthand way, although I don't know that it really is that much quicker to be honest. But people write the coefficient. We tend to use that in binomial theorem, the parentheses one. NCK we tend to use in the permutation and combination problems. But you could use it in either, and you'll probably see both in either. So 1 plus x to the power of n then, if I was to do the full expansion, would be nc0 plus nc1x plus nc2x squared plus so on and so on and so on, up to ncn x to the n would be the last term. Now, of course, 1 plus x limits us a bit. So if we now change it to just be a and b and generalise it a bit more, and then that idea of, okay, whatever the first one is, that's going to start at the power of n. And so a starts at the power of n. And then as we go along, the powers of A will go down by 1, the powers of B will go up by 1, but the two powers will always add to be the same. So the convenient way, when you look at it, it's nc0 a to the n, nc1 a to the n minus 1b. Whatever number's down the bottom will be the power of the b, and then the two of them have to add up to be n. So that's how you work it out. So if I've got 2 plus 3x to the power of 4, I could now expand it like so. I don't have to, although 4 I suppose is a pretty easy one to do for Pascal's triangle, but I don't need to. I can say, okay, well I know that's going to be 4c0, 2 to the power of 4, 4c1, power of 2 will go down by 1, so it's 3, power of 3x will go up by 1, so it's now to the power of 1. 4c2, 2 squared, 3x squared, and so on until we get to the last term. And we can go and calculate that out, and we come up with that beautiful expression there. Something about the number 216, it's very comfortable, I think. Some relationships that exist in Pascal's triangle. Here's the first one. nck is equal to n minus 1 ck minus 1 plus n minus 1 ck. That's basically the rule that allows us to create Pascal's triangle. To get any number, so if we're working on the nth row, we go to the row above, the nth minus 1 row, and add the two numbers immediately above it. So k minus 1 and k. So that's all that's really saying. We're going to prove it. 1 plus x to the power of n is 1 plus x times 1 plus x to the power of n minus 1. Now, the 1 plus x to the n minus 1, we now know we could expand that whole thing out. n minus 1 c0 plus n minus 1 c1x, and so on and so on and so on. So somewhere in the middle, there would be these two terms. n minus 1 ck minus 1 x to the k minus 1, and n minus 1 ck x to the k. Why have I just identified those two? Because I'm just interested in the powers of x to the k. So I know the 1 will be times the x to the k term, and the x will be times the x to the k minus 1 term. So if I'm just looking at the coefficients of x to the power of k, well, in the left-hand side, I know it's just nck. 1 plus x to the power of n, we said our expansion would be nck. The right-hand side, I'm going to multiply these ones together. Just interested in the coefficients, so I haven't bothered writing down the x. So 1 will be times the n minus 1 ck, and x, well, the coefficient of x is 1, it'll be times the n minus 1 ck, and we get n minus 1 ck minus 1, n minus 1 ck. But of course, they're going to be the same thing. It was just two different ways of working out x to the power of k. So those coefficients must be equal. So therefore, nck is indeed equal to those two added together. This one here is saying, well, Pascal's triangle is symmetrical. So nck is equal to ncn minus k. In other words, nc0 equals ncn. Move in 1. nc1 will equal ncn minus 1. nc2 will equal ncn minus 2. The two numbers on the bottom will add to give n. So if I said to you which one equals 5c2, the other one in that row that would be the same number would be 5c, 3. Got to add together to give 5. So that's the second little rule. This last one is merely saying, hey, we start and end with 1. So the first one, nc0, is always going to be 1, and the last one is always going to be 1. All right, 5b.